Okay, for you it's Tuesday, January 28th, I think. And probably two videos here today. What I want to go do is talk about accelerated motion again, because I didn't really describe the accelerated motion in a straight line the way I wanted. So the Earth's acceleration of gravity is 9.8 meters per second squared, almost 10. For the sake of today, let's call it 10. I'll let you use 10 on the test if you want. 10 meters per second squared. What does that mean? Well, meters per second is the speed. The fastest sprinters in the world can run 10 meters in a second. They're sprinting by, running 10 meters, another 10 meters, another 10 meters, let's say at a constant rate for several seconds. Well, Felix Baumgartner, as he was falling out of the sky, was going 10 meters per second faster every second. So if you were up there with him on the gondola when he was on top of that high altitude balloon and he jumped off and he disappeared into the distance, and you hit the stopwatch, at the end of 1 second, he'd be going as 10 meters per second, as fast as the fastest sprinters in the world can go. At the end of 2 seconds, he'd be going another 10 meters per second, 20 meters per second, which is about 48 or so miles per hour. 25 meters per second is about 55 miles per hour. So at the end of 1 second, at the beginning he's going 0 meters per second. At the end of the 1 second, he's moving at 10 meters per second. At the end of 2 seconds, he's moving 20 meters per second. At the end of 3 seconds, he's moving 30 meters per second, faster than a car, as fast as the car is going down I-75. At the end of 4 seconds, he's going 40 meters per second. At the end of 10 seconds, he's going 100 meters per second. 4 times faster than the speed limit. So within about 30 or 40 seconds, he goes faster than jets fly, faster than the speed of sound, by going 10 meters per second faster every second. That's his acceleration rate. Okay, well, I got one problem, and that is I gotta find my mouse, which is over here. Okay, so backing up, what I just talked about with Felix was the rate of change in velocity. And the way Felix did it was in a straight line, straight down, and that was the speed changing. But you can have the direction change, and that's what we're going to talk about today. Change in direction in motion. So let's go through some stuff. These were problems we did in the videos if you were doing them. Oops, nope, I already got past those, never mind. Okay. So we did not do, okay, so what does the downward slope in this graph mean? We talked about this. Let's see, we did 22, 23, and 24 on Monday. There we go, on the videos. So in this class, we could only deal with objects moving in one dimension, in one line, like Felix falling down or left to right. It takes higher math skills to deal with objects moving in 2 dimensions at once, like when I take this ball and throw it, it goes that way and this way in a trajectory. So we'll do that in physics class your senior year, for those of you that stick around. So they know how to do more complex solutions like these, but we can still talk about them without doing math problems on them. So we're going to talk about them qualitatively. We're going to talk about what they do. We aren't going to solve math problems on those ones that involve 2 dimensions. So 2 common examples are circular motion and projectile motion. And I just tossed this, and that was a projectile motion. A circular motion would be something that moves in a circle, like this. Hopefully I can get this to work. I have a weight here, and it can pull this string through this handle, and on the other end of the handle I've got basically something like a stopper. And I'm going to whirl this stopper around, and what will keep that stopper going in a circular motion as I hold on to this is this weight down keeps pulling it in a circle. And so I'll get that going in a circle, and if I get it going the right speed and let go of that weight keeps it in a circle. I also have to add some energy with whirling it about a little bit. But if I stop spinning it, the weight down here will just keep pulling that in. So I'm going to hold still, and it'll keep pulling it in farther and farther and farther and farther and farther until it stops. Well, the weight's on the floor, so. That's a circular motion. And there's a force that's associated with that, and an acceleration that's associated with that. So a circular motion, the acceleration is towards the center of that curve, and it is called centripetal acceleration. Now you might have said, no, I thought it was centrifugal. Centrifugal is fictitious. It doesn't actually exist. It's a phenomenon of inertia. That's probably a little over your head right now, but we will talk about that. It wants to go in a straight line. We keep pulling it in a circle. That is centripetal acceleration towards the center of a circle. If you were that object, you'd feel like you're going to the outside, but you're not. Earth experiences centripetal acceleration as it orbits the sun. It's not quite a circular path. It's a little bit egg-shaped, so we call it elliptical. But you know, if we're going this way and the sun's over there, it keeps pulling us in a big circle that it takes all year to get around. Projectile motion is anything that is thrown or shot through the air, and we're going to ignore air resistance in this because it makes things real complicated. So that projectile will follow in a curved path called a trajectory. In the absence of air resistance. So here's someone shooting a rubber band, and notice it goes this way, let's say at 2 meters per second, 2 meters per second, 2 meters per second, 2 meters per second, 2 meters per second. That speed stays the same this way if there's no air resistance. But its speed this way goes faster and faster and faster by a half meter per second every some time interval, maybe a tenth of a second or something. I don't know what the time interval is here. I could work it out, but I haven't done that. Notice, just like Felix, it's falling faster and faster and faster and faster. As a matter of fact, the fall rate would be the same as Felix's, almost 10 meters per second every whole second. So this is probably around a 20th of a second in here for that. So the vertical velocity increases by a regular amount of speed, not distance. The horizontal stays the same. So the horizontal velocity of a projected object keeps the same, as long as there's such a small amount of air resistance that we can ignore it. The vertical velocity increases by the same increment as long as your time intervals are the same increment. And it will match the vertical velocity that's falling without a horizontal velocity. I have a device that I'll try to tape. I don't have it on this, and maybe I'll do it on the next one quick, where it drops a ball and kicks a ball out at the same time. And they hit at the same time. Maybe I'll try to find somebody else's video. And that's what they're showing here on page 60. So what they've done here is have a red ball and a blue ball, and one gets shot out and one drops, and they go click at the same time. And they're in a dark room with a black background, and there's a flashing strobe light. And this was, a camera film was open, so this was been done on old school camera film. And every time the flash hits it, it records the ball, flash, 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 except it was probably like flash, 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 flash every 20th of a second or something like that. And what it's showing is the fall rate is the same. This one's going that way, but it doesn't affect the motion this way. They fall together. If I shot a bullet out here at the same time those two balls were released, at the same height, perfectly level, bang, that bullet would hit the ground at the same time, believe it or not, just way out there. So the horizontal velocity, the horizontal motion, and the vertical motion are independent of one another. If it's moving horizontally, it doesn't affect the vertical part. So let's take a look at the questions. Section 3 review, page 60. Page 60. Number 25 to 30. Describe the acceleration of your bicycle as you ride it from your home to the store. Well, you're going to start at 0 speed and then you're going to speed up, so that's an acceleration. And then you're probably going to go at constant velocity for a while. And then you're going to slow down, so that's a deceleration. So your acceleration would increase, and then you wouldn't have any acceleration while your speed's constant, and then your acceleration would decrease, probably. So it depends on your trip to the store. So let's say your bicycle speeds up with a positive acceleration at the beginning. During the trip, you may change speed a number of times. You may change direction a number of times. All of those would include forces, and they would all include changes in velocity. They would all include accelerations. So you may change speed and direction and accelerate several times, depending on your trip and where the store is and where your house is. At the end, though, you will slow down. That is a deceleration. It's also called a negative acceleration. It's an acceleration, it's just a negative number instead of a positive number like this one. Number 26. Determine the change in velocity of a car that starts at rest and has a final velocity of 20 meters per second north. Well, if it started at 0 meters per second and ended at 20 meters per second, the change is just 20 meters per second. That's not an overcomplicated problem. And the change in velocity is 20 meters per second. We have to give it a direction north. Number 27. Describe the motion of an object that has an acceleration of 0 meters per second squared. Well, you might think it's not moving. Aha. Its motion is not, magic word, changing. It will keep the same velocity, which means it will move the same speed and it will move the same direction. This object here, if I set it down, has no acceleration. And it's keeping the same velocity, happens to be 0, and its direction doesn't really have one because it's not moving. But the cars out on the highway out there that are going on straight level highway, they're not turning left or right, they're not going up or down, and their cruise control is set. Their acceleration is 0 meters per second squared also. But they're moving though. Their motion is not, magic word, changing. Number 28. Suppose a car is accelerating so its speed is increasing, kind of like Felix's speed was increasing for quite some time. First, describe the line you would plot on a speed time graph for the motion of the car. Then describe the line you would plot on a distance time graph. Okay, this is complicated. We're pushing it here. First of all, if it is accelerating, and if this is speed, and this is time, then the speed is getting more and 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 more as the time goes. And we can plot all those. In fact, in physics class we do. It's one of the first labs we do in the year. So it would make a line segment that slopes diagonally upward, and that is a positive slope, and they would all fall in a line because that velocity change is even if the acceleration is constant. And if, in our case, well, it doesn't say it's constant, but it would be a straight line segment if that was a constant increase in acceleration. Okay, on the distance time graph, it's going to be a curve. This graph is not on the test. So the speed time graph would give you a straight line as long as the acceleration is constant, and this you'll need to know. I'm not going to ask you about the distance time graph. It's going to give you a curve like this. And in physics class, we talk about this is the derivative of acceleration, and this is the integral of acceleration, and this is the integral of speed. And derivative of distance is speed, and the derivative of distance is acceleration. We actually don't calculate them as a calculus function, but we talk about that. So this one you won't need to know. I'm not going to put this graph on the test because this is good enough for us. Number 29, calculate the time. Balls dropped from a cliff, acceleration is 9.8 meters per second squared, almost 10. How long will it take the ball to reach a speed of 24.5 meters per second? We are going to use that equation from yesterday. Well, from Monday for y'all. So it's the change in velocity. This is supposed to be change in time. I'm not going to put that delta on there today, but it's supposed to be time minus time, which is a change in time. It's not supposed to be just t. Okay, so they give you 9.8 meters per second squared as the acceleration. That should go here. And they give you a speed of 24.5 meters per second. That should go here, and 0 went there because it started at rest. And we want to know the time this takes. Well, how do you solve this? Well, you should know by now. Yeah, we got to get this by itself, but the first problem we got to tackle is it's in a denominator. So we have to multiply by t to get rid of it, but to be equal, we have to multiply this side by t. Then we can continue. And once we do that, well, I subtracted this first, and then I got the t over there. And then t times 9.8 is equal to 24.5. Then all you have to do is divide both sides by 9.8, like this. 9.8 meters per second squared, and 9.8 meters per second squared. And then once you do that, you get t is 2.5 seconds, because one of these seconds cancels with that one. Meters cancels with meters. You have a second in a denominator of a denominator, which puts it in a numerator. So t is 2.5 seconds. Number 30, calculate speed. This time you have the acceleration, and you have 2 seconds. And we want to know the speed if the sprinter starts at 0. Okay? So there's your acceleration, 4.5 meters per second squared. There's the time, and v minus 0. So we'll just drop the 0 part off, bring the 2 up here, and it should come out to 9. So cancel the 2 over here. Go ahead and drop that 0 off. Seconds cancels one of those, and the speed ends up being in meters per second, which is right. So it should be 9 meters per second. Okay, I'm going to continue with another video.